In the last video, first part of derivative, we had gained some intuition of derivative or slope of a function. And in particular, we had seen how to calculate derivative using first principle. And we had seen it on examples of a linear function, a straight line, where the slope was constant at all the points of that line. And we had also seen an example of a constant function where the slope was always 0. So in this lesson, we will see some more complex functions. First of all, we will see it on a quadratic function, and we will see that slope need not be constant at all the points on the function. And then we will look at some non-polynomial functions like logarithmic or trigonometric functions. And finally, we will generalize our concept of straight line, that is linear function, constant function, or quadratic function to a generic polynomial function and how to calculate derivative or slope of that kind of function. So let's begin. So just as a brief recap, this was the derivative from first principle. In order to calculate that, if we have a curve and this is, let's say, point x, and this vertical axis denotes the fx, then if I want to calculate slope or derivative at this point x, then we nudge the value of x slightly to the right, that is increment its value. So we see what is the value for x plus h, and this will be fx plus h. So we subtract this, the difference in height, and we divide it by difference in width, which is h, and we get the derivative of fx at this point x. And this h should be infinitesimally small, that is very, very close to 0. Now let's see the example of x square, which is a quadratic function. This is not a straight line, and you can see if you calculate the slope here and at the bottom, with increasing x, the value of x square is not increasing much. For example, let's write a few values, and this is fx. So for 0, it's 0. For 1, it's 1. For 2, it's 4. For 3, it's 9. For 4, it's 16. So here you see that if I increase x by 1 unit, so here I have increased by 1, and this has gone up by 1. Now I increase it again by 1, but the difference here has gone up by 3, although I am increasing x by same amount. Now I increase it again by 1 unit, but the difference the x square difference goes up by 5 units, and similarly here 7 units. So although I am changing x by same, you see it's increasing, the value keeps on increasing. Difference is 1, difference is 1, then 3, then 5, then 7, it's increasing. So you can think that if I take any value of x and increment it slightly, this value will not be same as if I increment it here. Here it will be much more. You can see steep curve. Now let's use the first principles here. So x plus h square minus x square. fx is x square. So I change x to x plus h, so whole square, divided by h, and h is again infinitesimally small, and the way to represent is this h limit 0. So let's expand it. It becomes x square plus h square plus 2xh minus x square. X square goes away, h in denominator. So 1h cancels this, and 1h it cancels here. So it becomes 2x plus h. But as compared to x, the value of h is very small. So if x is 1, this entire term is 2, but this h will be very small, maybe 0.000, a large number of zeros than 1. So this will not impact this, and it will remain close to 2x. So for x square, f derivative of fx is 2x. And now you can substitute x for whatever value you want to calculate. So for x equal to 1, the derivative is x equal to 1, it will be 2. This is just alternate notation of this df x by dx. And now let's say I want to calculate it at 3. So this will be 2 times 3, which is 6. So at 3 it's more compared to at 1. So 1 is somewhere here and 3 is here. And you can see here the slope is like this and here it's like this. So clearly this is more steeper slope, and that's reflected in the formula as well. So the answer here is 2x. Now let's look at some non-polynomial function. So it's a logarithmic logarithm, natural logarithm of x. So this is equivalent to log base e x, and this is Euler's constant and its value is nearly 2.7, I think 72818 or something, or 71828, something like that. So close to 2.7. And if you're not aware of what is the meaning of log, then let me clearly explain here. So log AB, so here A is the base, log base AB. If let's say this value is k, then that means that A raised to the power of k is equal to b. Similarly here, log ex. So let's see in the graph where it is 1. You see that it's 1 here at this value. So I want, for what value of x, this will be 1. Let's say I want this. So what we said, this is equivalent, this whole term is equivalent to, so whatever is k here, right hand side, raise that to the power of base. Here base is e. So this is equivalent to e raised to the power 1 equal to x. E raised to the power 1 is simply e. So for x equal to e, which is here, it's 2.7. It should be equal to 1. And you see that for this value, it's 1. So this will be x equal to e. So now let's calculate the derivative. Its derivative is dy dx of, instead of fx, we will write ln of x. This is 1 over x. You can find the proof of this. You can prove it as well using, you can expand this term. So we will find ln 1 plus or h plus x minus ln of x divided by h. This is the derivative from first principle. Now log of a minus log of b is irrespective of base. If these bases are equal, these bases are same, then this will be log and the same base whatever you have used, a divided by b. And here it's natural logarithm. So here the base is e. So the numerator becomes ln h plus x divided by x, and denominator remains same. And this is again ln, this x goes away by 1. So we have 1 plus h over x in the numerator and h, and everywhere you have to write this limit. Now we can expand this term. There is an expansion. So let me write here log 1 plus x is approximated as Taylor series expansion of this is it's something like x minus 1 over 2x square plus 1 over 3 x cube minus 1 over 4 x4 and so on. So whatever is the even power of x, there is a negative there, and odd power of x, there is positive there. So instead of x, we have this h by x. So let's substitute that. So this is again base e, natural logarithm 1 plus x. So ln 1 plus h over x will be h over x minus h square by x square divided by 2 plus h cube by x cube divided by 3 and so on. And denominator is divided by h, and h is 0, close to 0, not exactly 0. So we can cancel one h term from all of these because h is divided here. So we will get 1 over x minus h divided by 2x square plus h square divided by 3x cube and so on. And since h is negligibly small, we will ignore all of these higher order terms and we are left with 1 over x. So d over dx of ln of x is 1 over x. So let's see some example. If x is 1, so if I take it for x equal to 1, it will be 1 since it's 1 over x. So let's see where is 1. 1 is here. So that means that if I draw a tangent to this point 1, then it will be at 45 degrees. This picture is not drawn to scale, otherwise you could have seen a tangent being at 45 degrees. And as x increases, this value will decrease. Let's say I want to find the slope at 2. So it will be 1 over 2, that is 0.5. So here it will be like this. And at 10, it will be 1 over 10, that is 0.1. That is very small. And you can see the line is, the tangent is becoming horizontal, going towards horizontal. Here it was more steep, then less steep, and now edging towards horizontal. If it perfectly becomes horizontal, it will be, slope will be 0. That will be true for very large value of x. Now let's see an example of some trigonometric function. So you can look at the exhaustive list on some Wikipedia page. What are the derivatives of different functions? So f dot dash x for sin x, dy dx of sin x is cos x, and dy dx of cos x is minus sin x. And these both sin and cos take values between -1 and 1. So they will always be oscillating between, this is the -1 line and this is +1 line. And these are in radians. At 90 degrees it's 1, and 90 degrees pi by 2 radians, that is 1.57. Since pi is 3.14, and you can see this value is very close to 1.57. 1 will be in the middle, and it's in the middle of these two. At 180 degree, that is pi or 3.14, it will be 0. Similarly at 0 it will be 0, and it will keep oscillating. It will complete its one oscillation in 2 pi. 2 pi is 360 degree. So 2 pi means 6.28. So this value will be 2 pi. And for cos, this is slightly different. Cos is 1 at 0, and where it becomes 90, it's 0. And if you relate it to derivative, that makes sense. We see that the derivative of sin x is cos x. That means the rate of change of sin x with respect to x at a given point x is cos x. So what is the rate of change of sin x here? The tangent will be a straight line, that is 0. and you see cos x is 0 there. At 0, its slope is like this, which looks very close to 45 degrees. So you can see cos x is here 1. Similarly here, tangent is horizontal, so it's 0. The rate of change of sin x. So you see cos x is 0 there. And you can similarly look for tan, cot, cosec and other trigonometric functions. So this was just to give you some idea. And now let's look at a generic polynomial function. We had already seen some examples of this. One was c, that is fx was constant, straight line. Then we had seen fx equal to x or 2x, where it was a line like this with some slope. Then we had seen x square, which was a curve like this. So we had seen these three examples. And you see all of these are general forms of this. First one is cx raised to the power of 0. X to the power of 0 is 1. Anything to the power of 0 is 1. And then 2x is 2 times x to the power of 1. And here we have 1 times x square. So here c is 1, n is 2. Here c is 2, n is 1. And here c can be any value. We had seen an example of 3. And n is 0. Now let's apply this to a generic polynomial function. And let's apply the first principle. So cx plus h raised to the power of n minus c x to the power of n divided by h. And h is infinitesimally small. So let's keep c common and expand this. So the way to expand a plus b raised to the power n is cn0 an b0 plus cn1 an minus 1 b1 plus cn2 an minus 2 b2 and so on. It will continue till cn n a to the power 0 b raised to the power n. So the sum of the powers is always n. 0 plus n is n, n minus 2 plus 2 is n minus 1 plus 1 is n plus 0 is n. This will be the expansion of this term. So for this also the same thing will apply. And this c n k, this will expand to n factorial divided by n minus k factorial. So what is the value of n0? It will be n factorial divided by n minus 0 factorial, that is 1. So first term is 1, last term is 1. This term will be, second term will be n cn1 equal to n factorial divided by n minus 1 factorial. So numerator becomes n times n minus 1 factorial divided by n minus 1 factorial. So this term cancels and we are left with n. And there will be higher order terms which we will ignore due to infinitesimally small value of h. So this becomes x raised to the power n, since cn0 is 1, and h to the power of 0, anything to the power of 0 is also 1, plus n times x n minus 1 h plus n minus 1 x h minus 2 h square, and the power of h is increasing. It will go on till hn. But we are ignoring higher order powers of h. So we will ignore all of these terms since these will be even smaller than h, and h is itself small. So we will take first two terms and divide by h. So we are left with c, and we have to subtract this second term. So c is common here, so minus xn, everything in bracket. So this xn goes away, and then we divide by h everything. So we are left with n x n minus 1 plus this h is cancelled. This will become h minus 2. Sorry, h, but we are not taking this term, so we can ignore that. So we are left with cn x to the power n minus 1. So the derivative of this will be c, the constant remains as it is, and this n comes, n is multiplied times x n minus 1. So you know the trick now. Whatever is the power, multiply it, bring it down, and decrement the power of this. So using this, let's take the example of x square. So what will be the final? Bring 2 in front. So bring 2 here. So 2x, decrement this n by 1, n minus 1. So 2x raised to the power of 1, which is same as 2x. So you see here, this is the same value. And now what will be for fx equal to x? So here the power is 1. So bring that ahead. So 1 times and decrement the power by 1. So earlier it was 1, now it becomes 0. So overall, the slope of fx equal to x becomes 1. So now you know how to apply it for any polynomial function. Let's do an exercise. What will be the slope of 5x raised to the power of minus 2? That is 5 divided by x square. And we can use the same formula, what we just saw. So whatever is here, bring it forward. So it's minus 2. So minus 2 times 5 is minus 10. And decrement it by 1. So it was minus 2, now it becomes minus 3. So it will be minus 10 divided by x cube. Now you see how quickly we have calculated it. We don't need to use first principles all the time. We can do it straight away. And this will be very helpful when you are dealing with polynomial functions. So I hope you got some good intuition of derivative, slope, and also seen some good number of examples, and you are ready to move further.